Let's look at question 18 of our physics examination revision question. Question number 18 says, the speed of a satellite in a stable circular orbit around the Earth is independent of the A. Universal gravitational constant, B. Mass of the Earth, C. Radius of the orbit, D. Height of the satellite above the Earth's surface, and then E. Mass of the satellite. So how do we provide the answer to this question? Let me come to this. So solution first. Solution. Now, to solve this question, I'll have to note two things. All right. I'll have to note two things. Number one, I'd have to recall from Newton's law of gravitation. All right. Before then, coming back to this question here, they mentioned satellite and they said the satellite is orbiting the Earth. All right. You have a satellite orbiting the Earth. From Newton's law of universal gravitation, we have that the force of attraction between the satellite and the Earth, F, is equal to G, that's the universal gravitational constant, times mass of the Earth, that's ME, then mass of the Sun, that's MS, all over the square of their distance apart. All right. So you want to note this where ME, that's ME, it's equal to mass of Earth, mass of Earth, MS is equal to mass of satellites. All right. And R, we said, is their distance apart. Okay. So we have this. Now, this is what we'll have from Newton's law of universal gravitation. Also, from the same question here, they said the satellite is orbiting the Earth. So you have the Earth, and then you have the satellite orbiting the Earth. If a satellite is orbiting the Earth, that means it moves with a particular force. All right. So let's say for orbiting satellites, that's this, you have that the force F is equal to mass times acceleration. In this case here, the acceleration here will be a centripetal acceleration. Why? Because the satellite is orbiting, is moving around the Earth, of course, in a spherical pattern, or let's say in a circular pattern. So we have this. But don't forget that AC, that centripetal acceleration, is equal to V squared all over what there? R. We have this. Okay. So with this, now since this is a satellite, F is equal to M, not just M, but what there? MS, mass of satellite, times centripetal acceleration. M is mass of satellite, then AC is centripetal acceleration. Since the satellite is moving in a circular path, so we have this. Now, if you work on this, we'll have that the force on the satellite F is equal to the mass of the satellite times V. Of course, V becomes the velocity of the satellite, of course. So V squared all over R, right? The velocity of the moving satellite times all over R. So we have this. Now we have force. This is the force according to Newton's law of gravitation. This is the force. When you consider Newton's second law of motion, we have this. If I equate F to F, if I equate this, equating F to F, what do we have there? From here, we'll have that this one here, that's mass of satellite, V of satellite squared all over R is equal to, from Newton's law of gravity, we have G, then mass of the Earth, then mass of the satellite all over R squared. From here, don't forget that in physics or in mathematics, whenever you have the same term on both sides of an equation, they can cancel out. So from here, mass of satellites can cancel mass of satellites. Okay. For two things to cancel out in an equation, one, they must be the same thing. Number two, they must be in the opposite side of the equation. Number three, they must be at the same place. By at the same place, I mean if I had Vs squared all over Ms times R being equal to G Me Ms all over R squared. In this case, Ms cannot cancel Ms. No, that would be wrong. Why? Because the Ms here is at the denominator Meanwhile, the ms here is at the numerator. All right, so you want to take note of this thing. So in as much as you must have the same term on both sides of an equation, they must also be at the same place. This is at the numerator, this is also at the numerator, so they can cancel out. All right, so from there, again, looking at this, we have arrow here, you also have arrow here, the same thing. So this arrow here gives you 1, cancels out. This arrow here gives you what there? R. In essence, from here, we have that the velocity or the speed of the satellite all squared is equal to g mass of the earth all over r. So we have this. Okay, let's get the speed of the earth. Vs will be equal to, of course, I'll have to take square root. The square root of g times mass of the earth all over r. All right, so with this, let's go back to the option there. So with this, what do we have here? They said the speed of a satellite in a stable circular orbit around the earth depends on, don't forget we said speed of satellite Vs is equal to the square root of g me all over r. They said is independent of what? Universal gravitational constant. Of course, it depends on this. So this is not the correct option there. They said mass of the earth. You can see that the speed here depends on me, mass of the earth. So this is not the correct option. They said radius of the orbit. That's r here, so you can see. So this is not the correct option. They also say the height of the satellite above the earth's surface. Of course, it depends, all right? Because it depends, because the farther, if you look at the height of the satellite from the earth's surface, the farther it is from the earth's surface, the more time it takes for it to move around the earth's surface. So this is not it there. But if you look at what we had mass of satellites initially, but you can see that mass of satellites at some point, which is at this point, they cancelled out. So it means the speed does not depend on the mass of the satellite. So for this question there, the correct answer should be mass of the satellites. This is your correct option. So option E is the answer to this question. Okay. All right, guys. So you now have, so that's the answer. All right, guys. So you now have question number 19 for yourself. All right. So here's your own assignment. It says a car is traveling at 7.0 meter per second. When the driver applies the brakes, the car moves 1.5 meters before it comes to a complete stop. If the car had been moving at 14 meters per second, how far would it have continued to move after the brakes were applied? Assuming the braking force in both cases is constant and the same. So you have your options here. All right, take your time, pause this video, solve this question, leave your answer in the comment section, and I'll tell if you're correct or not. All right. All right, guys. So as usual, if you enjoyed this video, don't forget to like this video. Okay, hit the thumbs up. All right, give this video a thumbs up. Also leave a comment. I gave you a task. All right, solve that question. Leave your answer in the comment section, and I will tell you if you're correct or not. Don't forget to also subscribe. If it's your first time here or you're yet to subscribe, please do what to subscribe. Hit the bell icon and select all so that you get notified whenever we upload new content. And finally, share this video to your friends and your colleagues so that they can also learn. Thank you and see you in our next class.